Okay, this is chapter 4, Polynomial and Rational Functions. Okay, we only look at the polynomial functions, and we only do the first 3 sections of chapter 4. So we only do 4.1, 4.2, and 4.3. So it's a relatively short chapter for us. Section 4.1, Polynomial Functions and Modeling. This is one of the few times that the modeling is not the word problems that we're used to seeing. These are not going to really be horrible word problems. Polynomial functions. Okay, we've actually seen these before. We didn't call them functions back then, we just said polynomials, but we've actually seen polynomial functions in terms of the linear and the quadratics. So definition. A polynomial function in x is a combination of sums and or differences of different whole number powers of x. Remember, the in x part just tells you that x is the variable. Okay, again, linear functions are polynomials, quadratic functions are also polynomial functions. So we have seen special cases of these before. Some examples of polynomial functions. F of x equals 8x minus 13. Remember, that graphed as a line. G of x equals 5x squared minus 12x plus 109. Okay, that was a parabola. And then something like h of x equals negative 56. Okay, the power of x is x to the 0 power. Remember, x to the 0 power would be 1. And this would be a horizontal line. We're now going to look at the general form of a polynomial function in x. So the formal form of a polynomial function in x is this. P of x for polynomial is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2, and continue on in the same pattern until you get down to a1x down to a sub 0. And notice simply sitting there would be the x to the 0 power. Okay, where n is a whole number. Remember, the exponents have to be whole numbers, which remember the whole numbers were 0, 1, 2, 3, 4, 5, and so on. So again, this is the formal form of a polynomial function. Again, something like 2x squared plus 3x plus 7, that would be a polynomial. And notice when we had the quadratic, we didn't use these subscripts on the a's, we just said ax squared plus bx plus c. The reason we're putting the subscripts on the a's is that we don't know how many powers of x we might have. We might have more than there are letters in the alphabet. There's nothing wrong with that. Let's have some terminology that goes with this. So terminology that goes with that formal form. Number 1, the numbers in a polynomial function are called the coefficients of the polynomial. Just like coefficients of a term, they're the non-variable part. The expressions between the plus and minus signs in the polynomial function are called the terms of the polynomial function. Remember, that's what a term was. It involved nothing but multiplication and or division. It was the stuff between plus and minus signs. Number 3, the degree of a polynomial function is the largest exponent on the variable. In the formal form, the degree is n. Now, because it's n has come to mean the degree. Just like we use m for slope, we use n for degree. Number 4, the leading term of a polynomial function is the term that has the largest exponent in the variable. The leading term includes the coefficient and the variable with its exponent. In the formal form, the leading term is a sub n x to the n. Notice if we write it in correct order, it's also the very first term. Number 5, the leading coefficient of a polynomial function is the coefficient of the leading term. In the formal form, the leading coefficient is a sub n. Now remember, the leading coefficient is a number, the leading term is a number and a variable. Number 6, the constant term of a polynomial function is the term that does not have a variable with it. In the formal form, the constant term is a sub 0. Number 7, a polynomial function is said to be in descending order if the exponents on the variables are decreasing as you read from left to right. For example, f of x equals 3x squared minus 9x plus 17 is in descending order. But that's the order we're used to. Okay, we're used to seeing the powers of x go down. Number 8, a polynomial function is said to be in ascending order if the exponents on the variable are increasing as you read from left to right. For example, g of x is equal to 1 minus 6x plus 5x squared is in ascending order. Okay, the powers of x go up. Remember, since it is a function, there is only one variable. Okay, some notes. Notes on the terminology. Number 1, if a polynomial function is written in descending order, then we have the following facts. First of all, the first exponent on a variable is the degree. If there is no variable in the function, then the degree is 0, unless the function is f of x equals 0. The degree of the polynomial function f of x equals 0 does not exist. The leading term is the first term. The leading coefficient is the first coefficient. And the constant term is usually the last term. If the last term has a variable, then the constant term is 0. There's always a constant term. There's always a leading term. Notice we're kind of giving special names to the first and last terms of the polynomial function when it's written in descending order. So all this applies when the polynomial function is written in descending order. Well, what happens if you switch it? If a polynomial function is written in ascending order, then we have the following facts. Number one, the constant term is usually the first term. If the first term has a variable, then the constant term is 0. Okay, again, don't say no constant term, say 0. The leading term is the last term. The leading coefficient is the last coefficient. And number 4, the last exponent on a variable is degree. If there is no variable in the function, then the degree is 0 unless the function is f of x equals 0. The degree of the polynomial function f of x equals 0 does not exist. We actually had degree way back in Chapter R the first time we saw polynomials. Back then we talked about polynomials in general, not just polynomial functions. Now we're looking at functions. Let's try some examples. For each of the following polynomial functions, find in Part A the degree, Part B the leading term, Part C the leading coefficient, and Part D the constant term. So our first one, I've got f of x equals 7x to the fourth minus 9x cubed plus 11x squared plus x minus 13. Okay, notice it is written in descending form. So the degree, remember, it's supposed to be the largest exponent on a variable. Okay, largest exponent on a variable. Don't look at exponents on numbers, but exponents on variables. So the degree is 4. Okay, the leading term, it's supposed to be the term that has the largest exponent on a variable. In this case, 7x to the fourth. Okay, the leading coefficient is supposed to be the coefficient of the leading term, 7. And the constant term, it's supposed to be the term that doesn't have the variable. Now don't lose the minus sign on the 13. So the constant term is minus 13. So it just comes down to knowing what the words mean. Number 2, g of x is 3x minus 11x squared plus 18x cubed plus 10. Okay, notice this one is in neither descending or ascending form. It's just kind of scrambled up. Okay, remember the degree, the largest exponent on a variable. So in this case it's 3. Okay, the leading term is supposed to be the term that has the largest exponent on the variable. In other words, it's the term that gave you the degree. In this case, 18x cubed. Leading coefficient, the coefficient of the leading term, 18. And Part D, the constant term, the term without a variable, 10. Number 3, h of x is equal to x minus x to the 7th. Okay, this is actually an ascending form. So our degree, the largest exponent on a variable, 7. The leading term, the term that gave us the degree, minus x to the 7th. The leading coefficient, okay, the leading coefficient is understood to be minus 1 there. So minus 1. Okay, the constant is supposed to be the term without a variable. All the terms have variables, so the constant term is 0. Again, 0. Don't say no constant term or does not exist. It's 0. The constant term and the leading term must exist. Now, by the way, constant term and constant coefficient are kind of interchangeable. We usually just say constant. And number 4, k of x is equal to 56. Okay, remember, all numbers except for 0 have degree 0. So this is degree 0. Okay, the leading term, well, the only term we have is 56. So the leading term is 56. The leading coefficient, again, the only thing we have is 56. So the leading coefficient is 56. The constant, well, once again, the only thing we have is 56. So the constant is 56. When it's a constant valued function, that constant is the leading term, the leading coefficient, and the constant term. Write each of the following polynomial functions in Part A descending order, Part B ascending order. Okay, so we're doing descending and ascending. Okay, here's our first one. I've got f of x equals 9x minus 6x squared plus 12 minus 4x cubed. Okay, when we're descending order, the exponents on the variables are supposed to go down. So if I do it in ascending order, it would be minus 4x cubed minus 6x squared plus 9x plus 12. Okay, the ascending order, just reverse it. It's going to be 12 plus 9x minus 6x squared minus 4x cubed. Let's try one more of those. We've got g of x equal 8x minus 12x to the 6th minus 13 plus 5x to the 9th plus 5x squared. Now if we were doing descending order, 5x to the 9th minus 12x to the 6th plus x squared plus 8x minus 13. The powers of x should go down. Okay, for the ascending order, just reverse it. Negative 13 plus 8x plus x squared minus 12x to the 6th plus 5x to the 9th. Okay, now some special names for polynomial functions. You need to know their names. Okay, you do need to know their names. So special names for polynomial functions. It's based upon the degree. Okay, the degree is going to give you the special name, and we're going to look at what is kind of the generic form of the graph. Okay, degree 0. The form is f of x equals c. Okay, it's called a constant value function. It's a horizontal line. Okay, horizontal line. Okay, degree 1. It's f of x equals mx plus b. It's linear. It's a line. Okay, notice we don't use that a sub n, a n minus 1 nonsense. We actually use the letters we're used to seeing. You know, mx plus b. And for the degree 2, that's f of x equals ax squared plus bx plus c. It's called a quadratic. Remember, the graph is parabolas. That's what we looked at in chapter 3. Our next degree, 3. It's f of x equals ax cubed plus bx squared plus cx plus d. It's called a cubic. The graph is sigmoid, which means S-shaped. You sometimes kind of have to use your imagination to see the S, because the S is kind of on its side. Okay, degree 4 also has a name. It's f of x equals ax to the 4th plus bx cubed plus cx squared plus dx plus z. It's called quartic. It's either a w, an m, a u, or a u upside down. Okay, if you think about an m as a w upside down. So again, these are the basic shapes of it. And the last one with a name is degree 5. It's f of x equals ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus cx plus f. The name is Quintic. Okay, Quintic. The graph, there are really too many shapes to list them all. But those are the ones with special names. And again, you do need to know their special names. If you're good with your prefixes, you will get their names. Okay, the leading term test. Okay, it's sometimes called the leading coefficient test, but you actually do need the entire term. So we need some terminology about graphs. Okay, about graphs in general, but it mainly applies to the polynomial functions. So this would actually be what would be sigmoid shaped. Okay, this side on the left, which keeps going down, we call it the left end. This piece that's on the right, we call it the right end. Okay, it just keeps going up. This one keeps going down. So in the previous picture, again, this picture right here, in the previous picture, we would say the end behavior is left end down and right end up. We could also describe it as left end falls and right end rises. So down and falls, up and rises. I tend to say down and up. The book tends to say falls and rises. So again, going back to the slide, this is the left end, it's down, and this is the right end, it's up. Okay, so pretty tricky. In the next picture, we could describe the end behavior as both ends up or as left end up and right end up. Now again, the book would probably say both ends rise or left rises, right rises. The classic parabola. So the left end is up, the right end is up. If the parabola were upside down, both ends would be down. And that's the end behavior. Okay, we can now state the leading term test. Let p of x be a polynomial function with leading term a sub n x to the n. Okay, I actually had to give it a name so we could talk about stuff with it. Then, okay, we have two cases, and each one of the two cases has two subcases. Part A, if n is even, so an even degree polynomial function. The classic example is f of x equals x squared. If a sub n is greater than 0, then both ends are up. Now again, the classic example is f of x equals x squared. If a sub n is less than 0, then both ends are down. The classic one there is f of x equals negative x squared. So with an even degree polynomial function, the ends are in the same direction. They're both up or they're both down. What about odd degree? So part B, if n is odd degree. So an odd degree polynomial function. Number one, if a sub n is greater than 0, then the left end is down and the right end is up. Okay, the classic example there is f of x equals x. Number two, if a sub n is less than 0, then the left end is up and the right end is down. The classic example there is f of x equals negative x. Okay, for an odd degree polynomial function, the ends are in opposite directions. One up, one down. Okay, so odd degree, one up, one down. Even degree, both up or both down. Let's try some examples. Determine the end behavior of each polynomial function. So we're going to say, left end, right end, up or down. Here's our first one. F of x equals 8x to the fifth minus 9x to the fourth plus 11x cubed plus 15x squared minus 8x minus 10. Here we're going to show you kind of a quick and dirty way to determine the end behavior rather than trying to memorize those cases. But it is degree 5. It's odd degree, so they're going to be in opposite directions. So for the left end, we choose a number less than 0. Okay, that's what we mean by the left and right. To the left of 0, which is to the left of the y-axis, and to the right of the y-axis. I want to pick x to be negative 1. Okay, so just substitute negative 1 into the leading term. So don't worry about this other nonsense. We're not trying to graph it. I'm just trying to figure out, do I get a positive or a negative result? So we'll have 8 times negative 1 to the fifth. That's negative 8. You take negative 1 to an odd power, it's negative. Okay, negative 8 is the end result for the leading term part. So negative is down. So the left end is down. For the right end, choose a number bigger than 0, like 1. So notice I'm always going to pick negative 1 and 1 for the leading term test and just plug it into the leading term. So I'm going to have 8 times 1 to the fifth, which is 8, because 1 to any power is just 1. Okay, that's positive. Positive is up. So right end up. That's all you do. Pick x equal negative 1 and x equal 1. Negative 1 is for the left. Positive 1 is for the right. And just substitute those values into the leading term. If you get a negative result, that's down. If you get a positive result, that's up. So our final answer, left end down and right end up. This does kind of help you to graph it. That means our graph is starting from the bottom like this and then somehow wiggling and then eventually going up. Okay, a polynomial function only crosses the x-axis a finite number of times. Then it leaves it forever. Number 2, I've got f of x equal negative 7x to the 8th minus 14x to the 7th plus 11x squared plus 108. Okay, it is even degree, so both ends will be up or both ends will be down. So for the left end, again, plug x equal negative 1 into the leading term. Okay, negative 1 to the 8th is positive 1 times negative 7 gives me negative 7. Negative result, that's down. For the right end, negative 7 times 1 to the 8th. That's also negative 7. Negative and negative results, both ends are down. Remember, if you take negative 1 to an even power, it's positive. If you take negative 1 to an odd power, it's negative. And of course, 1 to any power is still just 1. Number 3. Okay, negative 3 times x squared minus 8 to the fifth minus 5x cubed plus 4 to the fifth. Okay, we have to figure out what is the leading term. So hidden inside of this example is a separate question of finding the leading term. Okay, notice we do have it in factored form, which would be great if we were looking for zeros. Okay, so what we're going to do is inside of each one of the factors, we look at the leading term or first terms. By the way, the leading term is sometimes called the first term, even if it's last. So this factor, its leading term is negative 3. This one, its leading term is x squared, and this one is negative 5x cubed. So we need to find the leading term. So again, that's kind of the little sub-problem that's in this problem of what is the leading term. So we multiply out the first terms, or the leading terms, of each factor. Okay, don't forget the negative 3. So we'll have negative 3 times x squared to the fifth power, right? Minus 5x cubed to the fifth power. Okay, remember, for a power to a power, you're multiplying the exponents. Okay, and you're just going to have to do negative 5 to the fifth power, kind of crunch that out. So it's going to give me an x to the 10, that'll give me an x to the 15. So I have negative 3 times negative 5 to the fifth times x to the 10 plus 15, which gives you 9,375 times x to the 25th. Okay, again, I did negative 5 to the fifth times negative 3 to get 9,375. Okay, so that's the leading term. So if you were asked, what is the leading term of this polynomial? There it is. Okay. For the left end, let x be negative 1. So I'm going to have negative 1 to the 25th is negative 1 times now 1,375 is negative 9,375. For the right end, 1 to the 5th is 1, so I end up with 9,075. So left end down, right end up. Remember, negative is down, positive is up. Okay, let's try one more like that. So I've got f of x equals x squared times 5 minus x cubed to the 4th times 2x to the 5th plus 3 raised to the 5th power. Okay, notice this one is written in ascending order. So its leading term is going to be the negative x cubed. So find the leading term. So I've got x squared for this guy, negative x cubed to the 4th for this one, right? This is the leading term, the last term, because it's in ascending order to the 4th power, and then 2x to the 5th to the 5th. Okay, that's going to give you an x to the 12th. Okay, if you take negative 1 to the 4th power, it's positive 1, and then we'll have 2 to the 5th, and that's going to be an x to the 25. Okay, 2 to the 5th is a 32. Negative 1 to the 4th power is 1. Okay, and I have 2 plus 12 plus 15. So I'm going to have 32, x to the 29. Excuse me, x to the 39. So then, for the left end, 32 times negative 1 to the 39th is negative 32. Remember, negative 1 to an odd power is negative. For the right end, 32 times 1 to the 39th is going to be 32. That's down, that's up. So remember, to get the leading term when it's in factored form, you do the product of the leading terms of each factors, and then don't forget the exponents outside parentheses. Multiplicity. Okay, multiplicity. The definition and terminology. What exactly is it? Definition. Let f be a function. Okay, now for us it's polynomial functions. The number x equals c is called a zero of multiplicity k with k greater than or equal to 1 if and only if x minus c to the k is a factor of f of x, but x minus c to the k plus 1 is not a factor of f of x. Now you're probably wondering, what does that really mean? So this means that if you completely factor f of x, the x minus c occurs as a factor k times, like x minus c to the 5th, or x minus c squared, or just x minus c to the 1st power. Okay, so it comes down to your ability to factor. Okay, that's really what it is, it's your ability to factor. And it's how many times does x minus c occur as a factor. So the number of times x minus c occurs as a factor, that's the multiplicity of the number x equals c. Some terminology. Number 1, if k is equal to 1, then the 0 is called a simple 0. Okay? So its multiplicity 1 is a simple 0. If k is equal to 2, then the 0 is called a double 0 because it occurred twice. You could also say triple 0 if k is 3. And if k is any value greater than 1, then the 0 is called a multiple 0. So it's kind of like we have simple zeros and multiple zeros. Now again, in order to get the zeros, you need factors, because we've actually looked at getting zeros before. We just now have this new concept of multiplicity, and that is how many times does the factor appear in the factorization. Let's try some examples. Find all the zeros of each polynomial function and state their multiplicities. F of x equal to x squared minus 5x plus 4. Okay, it's not factored. We have to factor it. So it's kind of like you're doing the first step of getting the zeros here, which is factorization. So I've got x squared minus 5x plus 4 equals 0. I want factors of 4 that add up to be negative 5. It's negative 1 and negative 4. So I get 4 from this one and 1 from that one. And notice, each factor only appears once. So each 0 has multiplicity 1. So x equals 4 is multiplicity 1. Again, the factor only appears once. X minus 1 has multiplicity 1 because, again, it only appears one time. So before we would have just said the zeros are 4 and negative 1, we would have stopped. Okay, notice, if you add up the multiplicities, it's the degree of the polynomial. That will always be true. Okay, The sum of the multiplicities has to equal the degree of the polynomial. Number 2. Okay, it is factored. Okay, so I have f of x equal 8x to the 4th times x plus 11 to the 12th times x minus 5 to the 3rd. Okay, don't multiply it out. Remember, we want to use the factors to get the zeros. Okay, now don't forget the first factor of 8x to the 4th. So I get 0. X to the 4th appeared 4 times, the multiplicity is 4. Okay, from x plus 11, the 0 is negative 11, the multiplicity is 12. From x minus 5, we get 5, and the multiplicity is 3. Notice, it's better to work with factored form. Most of the time I'll give it to you in factored form with one exception, the linears and the quadratics. Remember, the quadratic, if it doesn't factor, we would use the quadratic formula. And number 3. I have f of x equals 3 times x plus 10 to the 7th times x minus 6 to the 4th times x squared minus 5x plus 6 all to the 8th. Okay, this quadratic, we can probably factor it. Multiply to be 6 and add up to be negative 5. It's got to be negative 3 and negative 2. So we're going to factor the trinomial. Okay, it factors as x minus 3 times x minus 2. And both of those factors to the 8th power. So let me drop these outside parentheses. So I'm going to have 3 times x plus 10 to the 7th times x minus 6 to the 4th times x minus 3 to the 8th times x minus 2 to the 8th. Okay, so the quadratic, we factored it. The exponent outside parentheses on it applies to each one of its factors. Okay, now we're looking for the 0. Remember, the number 3 cannot be set equal to 0, so we ignore it. From x plus 10, we get negative 10, multiplicity 7. From x minus 6, I get x equals 6, multiplicity 4. Remember, you're setting each factor to 0. So what makes x minus 3 0 would be 3, multiplicity 8. What makes x minus 2 0 is x equal 2, multiplicity 8. And that's your answer. Remember, multiplicity is just a number. So even and odd multiplicities. Okay, consider the following two functions and their graphs. Okay, I'm going to make it kind of easy for us. I've got f of x equal x minus 2 squared, and g of x equals x minus 2 times x plus 3. Now notice for both of them, x equal 2 is a 0. In f of x, the multiplicity is 2. In g of x, the multiplicity is 1. So both functions have x equal 2 as a 0. Again, we can see that because of the factored form. For f, x equal 2 has even multiplicity. And for g of x equal 2 has odd multiplicity. Again, multiplicity 2, which is even, multiplicity 1, which is odd. Okay, here are their graphs. Okay, remember, they're both parabolas. Because if you were to square them out and do FOIL, you're going to see an x squared. So there's f of x equals x minus 2 squared, and this is g of x equals x minus 2 times x plus 3. Okay, they're crossing x equal 2 here, but for f of x, it's touching. This is touching, this is crossing. Now some people refer to this as it bounces, it comes down, hits the the x-axis, and bounces up again. So, but this is touching, this is crossing. This had even multiplicity, this had odd multiplicity. So the graph of y equal f of x, which equal to x minus 2 squared, is tangent to the x-axis. Okay, that's the technical name. Tangent, touching, bouncing. The graph of y equal g of x equals x minus 2 times x plus 3 crosses the x-axis at x equal 2. Okay, and remember, this one had the even multiplicity, this one had the odd. Even was tangent, odd was crossing. So this little fact leads to, let x equals c be a 0 of f of x. Okay, now this works even for non-polynomial functions. If x equals c has even multiplicity, then the graph of y equal f of x is tangent to the x-axis at x equals c. And number 2, if x equals c has odd multiplicity, then the graph of y equal f of x crosses the x-axis at x equals c. So even is tangent, odd is crossing. If x equals c is not a 0 of f of x, then the graph of y equal f of x is neither tangent to the x-axis at x equals c, nor does it cross the x-axis at x equals c. So we have tangent, crossing, and neither. Let's try some examples. For the given function f and the given value of c, determine if the graph of y equals f of x is tangent to the x-axis at x equals c, crosses the x-axis at x equals c, or neither. So this is kind of multiple choice. So here's our first one. I've got f of x equals 3x squared times x minus 7 to the 5th times x plus 4 to the 8th. So I've got it factored for you. Okay, most of the time, again, I will factor it. I don't want you straining your brain trying to factor it. The one exception will be the quadratics. Okay, and my value of c is 7. So 7 has odd multiplicity. It makes x minus 7 equal to 0. That's all you check. Does it make a factor equal to 0? Okay, odd multiplicity. The exponent on the factor is 5. Remember, odd multiplicity is cross. So it crosses the x-axis at x equals 7. Number 2, it's the same function. F of x equals 3x squared times x minus 7 to the 5th times x plus 4 to the 8th. But my value of c has changed. My value of c is now 4. Okay, again, you're asking yourself, does the value of 4, does it make any factor equal to 0? No, no, no. So 4 is not a 0 of f of x. So that of f of x. That means it's neither crossing nor tangent. Remember, it has to be a 0 first. Number 3, same function again. F of x equals 3x squared times x minus 7 to the 5th times x plus 4 to the 8th. My value of c is now 0. Okay, my value of c is now 0. Does x equal 0 or does c equal 0 make any factor equal to 0? Right there, 3x squared. 0 squared is 0. Exponent is 2. So c equals 0 has even multiplicity. That means it's tangent to the x-axis at x equals 0. Remember, even is tangent, odd is crossing, and if it's not a 0, it's neither crossing nor tangent. Number 4, I've got f of x equals 4x minus 3 to the 7th and times 2x minus 1 to the 6th. And my value of c is 4/3. Again, we're going to check to see, does 4/3 make a factor equal to 0? 4 times 4/3 is 16/3, and 16/3 minus 3 is not 0. 2 times 4/3 is 8/3, and 8/3 minus 1 is not 0. So it's not a 0 of f. So it's neither crossing nor tangent at x equals 4/3. I've got one more. It's going to be the same function as there, but I'm going to change my value of c. So f of x is 4x minus 3 to the 7th times 2x minus 1 to the 6th. And this time my value of c is equal to 3/4. Again, we're wondering if we plug in 3/4, I get 0. Okay, 4 times 3/4 is 3. 3 minus 3 is 0. Odd multiplicity. So 3/4 has odd multiplicity, because of the 7. Remember, odd means it's crossing. It crosses the x-axis at x equals 3/4. Okay, let's look at our polynomial models. Okay, so polynomial models. Okay, it's not the awful word problems that we've had before. Let's face it, we've had some hideous word problems. Number 1, the height in feet of an object, t seconds traveling thrown into the air, is given by s of t equals negative 16t squared plus 108t plus 24. Find the height of the object 5 seconds after it is thrown into the air. Okay, unlike all our previous problems, this is not our word problems. This is not making us do something fancy. We just have to plug in t is equal to 5. So we're going to find s of 5. So this is a fancy way of saying evaluate the polynomial. So I'm going to have negative 16 times 5 squared plus 108 times 5 plus 24. This is just evaluating an expression. So I'm going to have negative 16 times 25 plus 540. That's what 108 times 5 is, plus 24. Okay, negative 16 times 25 is going to be negative 400, then plus 540 plus 24. You crunch all that out, and you get 164 feet. That's how high the object is 5 seconds after you throw it into the air. So notice, compared to some of our previous word problems, this is really not too bad at all. Okay, let's try one more. The number of Three Stooges fans in the U.S. has shown a steady increase in recent years. The number of Three Stooges fans in the U.S. since the year 2001, measured in hundred thousands, can be modeled by f of x equals 0.02x squared plus 1.56x plus 3.2. Using this model, how many 100,000 Three Stooges fans were there in the year 2007? Now remember that function measures the number of fans since the year 2001. So we have to figure out how many years are there between 2001 and 2007. So we need to find x first. It's going to be 2007 minus 2001, which is 6. So we need to find f of 6. So the thousands of fans will be, actually should be 100,000, that will be f of 6, which is 0.02 times 6 squared plus 1.56 times 6 plus 3.2. We get 13.28 hundred-thousand. Okay? And that's your final answer. So these modeling problems are really just fancy ways of making you say evaluate a function. That's the end of section 4.1.